The symbol integral of f of x dx means find the antiderivative of whatever is between the integral sign and the dx. Let's take a look at 1a. Here we have integral of 2x dx. If you think of the integral and the dx as bookends, what's in between is some function, and you ask yourself the question, what function did I have to differentiate in order to get 2x as the result? That's really very easy. You know that 2x is the derivative of x squared, so the answer should be the antiderivative of 2x dx is simply x squared. However, you have to think one more moment and say, if I had had x squared plus any constant, when I took the derivative of that constant, I would get simply an extra 0. So in fact, the most general antiderivative for 2x is x squared plus c, where c is any constant whatsoever. Now, that's the simplest one. If we walk down to 1b, we see the integral of x cubed dx. Here we want to find the antiderivative of x to the third power. That is, we have to ask, what kind of function would we have to take the derivative of so that the result would be x to the third power? It seems that the answer should involve x to the fourth power, because we know when we take the derivative of x to the fourth power, we get an x cubed. But what we get is 4x cubed. So in order that we not be off by a constant multiple, what we have to do is write this as 1/4 of x to the fourth power. Now if you take the derivative, the 4 comes down, cancels the 1/4, and you get simply x cubed. But don't forget, even in this case, you can add any arbitrary constant. So the integral of x cubed dx is 1/4 x to the fourth plus c. Now, unfortunately, finding antiderivatives is not as easy as finding derivatives. There are very few rules that tell you how to find antiderivatives. You've got to attack each problem almost as a challenge. There are 3 formulas that we know that we certainly can use, and let me summarize those for you. In general, the integral of x to the nth power dx is going to equal 1 over n plus 1 times x to the n plus 1 plus c, as long as n does not equal minus 1. Do you see why? When you take the antiderivative as we did here for x cubed, you have to raise the power by 1 to get the antiderivative. In order that you not get a constant multiplier, you have to divide by that same power, namely 4. So if this were x to the nth, you would have here n plus 1, and you'd be dividing by n plus 1. Therefore, you would not want n to equal minus 1, because of course that would mean dividing by 0. Now, what other rules do we have from derivatives that could be applied to integrals? Well, there's this. The integral of cf of x dx, that is, the integral of a constant times f of x dx, is the constant times the integral of f of x dx. Why? Because when you take the derivative of a constant times a function, you simply carry that constant multiplier. And finally, if you have the integral of the sum or difference of 2 functions, you can take the integral of each piece separately and add them together. All right, let me say that again. The integral of x to the n dx is equal to 1 over n plus 1, x to the n plus 1 power, plus c, if n does not equal minus 1. The integral of cf of x dx equals c times the integral of f of x dx, and the integral of f of x plus or minus g of x dx equals the integral of f of x dx plus or minus the integral of g of x dx. All right, let's try to apply these formulas to part C of problem 1. In problem 1c, we have the integral of 4x to the 15th power plus 8x to the minus 7th power dx. According to these formulas, first of all, we can look at each piece separately. That is, we have this plus this, and we can simply take the integral of each piece as a separate function. Secondly, we know that the constant multipliers are simply going to be carried along as constant multipliers. So the integral of 4x to the 16th is going, x to the 15th, sorry, is going to be 4 times x to the 15th, when I take the antiderivative, becomes 1/16 of x to the 16. The next term, we have 8 times the antiderivative of x to the minus 7th. Now remember, we have to raise the power 1. X to the minus 7 plus 1 is x to the minus 6. And remember, we have to put that fraction out in front. So it's 1 over minus 6 times x to the minus 6. And we add that famous arbitrary constant at the end. Now this can be simplified. The fraction can be knocked down, so this is 1/4. And here we could divide by 2, making this 4 and this minus 3. And the final result, maybe I'll squeeze it up here for you, is 1/4 x to the 16th minus 4/3 x to the minus 6 plus c. Let's go down to 1d. In 1d, we have the integral of a fraction, x to the 5th minus 3 times the square root of x plus 2 divided by x cubed dx. We have no rule for finding the antiderivative of a quotient. So this is really a big problem. However, in this particular case, we're able to use some algebra to help us out. First of all, we'll replace the square root of x by x to the 1/2 power, which is really the same thing. And now what I have is x to the 5th minus 3 times x to the 1/2 plus 2, the whole thing divided by x cubed, which means that I can really divide each term in the numerator by x cubed. If I divide each term by x cubed, I get the integral of x to the 5th divided by x cubed is x squared, minus 3 times, now, x to the 1/2 divided by x cubed, that's x to the 1/2 minus 3, which is minus 2.5 or minus 5/2. So this is x to the minus 5/2 power plus 2 divided by x cubed. That's 2 times x to the minus 3 power. All times dx. Now, inside these parentheses, every term is one that we know how to find the antiderivative of. Each one is something of the form x to the nth power multiplied by a constant. Let's see if we can use these formulas. The antiderivative of x squared, that becomes x cubed, so it becomes 1/3 x cubed. Minus 3 times, now when we add 1 to minus 5/2, we're taking the antiderivative of x to the minus 5/2, that becomes x to the minus 3/2, which means we have to divide by minus 3/2. Dividing by minus 3/2, that's the same thing as multiplying by minus 2/3. So this becomes minus 2/3 times x to the minus 3/2 plus 2 times, and now we have x to the minus 3, the antiderivative. We add 1 to the exponent, becomes minus 2. Remember, we have to divide by that, so it becomes 1 over minus 2 times x to the minus 2, and finally plus c. Now let's try to do a little bit of simplification, because a lot of these fractions are going to go out, and we get 1/3 x cubed minus 3 times minus 2/3 becomes plus 2 times x to the minus 3/2 plus 2 times 1 over minus 2. That's going to cancel and give you just a minus 1. So this is minus x to the minus 2, and finally plus c. One more thing I want to say before I leave this is the following. The first formula we gave you was the integral of x to the n dx equals 1 over n plus 1 times x to the n plus 1 plus c if n is not equal to minus 1. Now, if we were to change that formula to integral of u to the n du equal 1 over n plus 1 u to the n plus 1 plus c, if n does not equal minus 1, we actually have the same formula. We've simply changed x's to u's. That may sound like we've done nothing, but as you're going to see in parts E and F, that turns out to be very important. Remember, integral of u to the n du is equal to 1 over n plus 1 times u to the n plus 1 plus a constant, as long as n does not equal minus 1. Now, let's see how this formula can be applied to problems such as 1e. In 1e, we see the integral of 3x plus 1 raised to the 10th power dx. Now, in theory, I could do this problem by multiplying this out, but it would take a long time, and I'd have an enormous polynomial that I could integrate term by term. However, there is an option, and the option is this. If I think of 3x plus 1 as u, then what I have here is u to the 10th power. That's of the form u to the n. However, if I want to do the integral of u to the n, I must have du, not dx. So I think as follows. I think u is 3x plus 1. If u is 3x plus 1, then du, what's du? The differential of u is, how do you find a differential? You take the derivative and multiply it by dx. So the differential of u is 3 times dx. Now let's go back up to the integral. This is u to the 10th. If I had here 3 times dx instead of dx, I would actually have u to the 10th du. So what I'm going to do is I'm going to put a 3 in there. I'm going to rewrite this integral as integral 3x plus 1 to the 10th times 3 dx. But that's not fair. I can't just multiply by 3. I've made everything 3 times as large. In order to keep it honest, I have to divide by 3. That means I have to multiply by 1/3. Now, here's the advantage of knowing that a constant times a function can be integrated and factor out the constant. Let me say that again. The integral of cf of x dx is the same thing as c times the integral of f of x dx. That means the 1/3 that I need to cancel this 3, I can put outside the integral, so that the integral I started with, integral 3x plus 1 to the 10th dx, is exactly the same as 1/3 the integral of 3x plus 1 to the 10th times 3 dx. And this is u to the 10th times du. And that I can use my formula for. And what do I get? Well, I have 1/3 here. The integral of u to the 10th is 1/11th times u to the 11th. U is 3x plus 1. So that's 3x plus 1 to the 11th power. And of course, I add a constant to the end. And I rewrite this as 1 over 33 times 3x plus 1 to the 11th plus c. Of course, if you really want to, you can check that answer by taking the derivative of this result. Remember, we did an antiderivative, and you should really take the derivative at least the first few times and make sure that when you take the derivative, you get back the original function, in this case, 3x plus 1 to the 10th. All right? Let's move over to part F. In part F, we have the integral of 5x times the square root of 1 plus x squared dx. Well, again, the first thing we're going to do is get rid of that square root sign. So I'm going to rewrite this as the integral of 5x times 1 plus x squared to the 1/2 power times dx. Again, I would like this to be in the form u to the nth power times du. That 2 is a little hard to read. Let me write that larger. I would like this to be in the form u to the nth power du. Now, if I want to do that, what am I going to have to call u? I'm going to have to let u be 1 plus x squared. If I let u be 1 plus x squared, then du is going to have to be what? The derivative of this is 2x times dx. Well, let's go back and look at the integral. I have a 5 times x times dx. If I were to bring it over here, I can do that, right? I can multiply things in any order. So I can bring the 5x over here. I don't really want 5x, I want 2x. So what I'd like to do is change 5x dx into 2x dx. How am I going to do that? I've got to divide by 5 and multiply by 2. In other words, I have to write this as the integral of 1 plus x squared to the 1/2 times 2x dx. Now remember, I really had 5x dx. So in order to have the same result, I have to put out here 5 over 2. Let me check that. 5/2 times 2 is 5, so I really have back the integral of 5x dx times 1 plus x squared to the 1/2 power. And now I'm in the form u to the 1/2 du. So I can take the antiderivative. This is 5/2. Now, u to the 1/2, add 1 when you take the antiderivative, so it becomes u to the 3/2. Then you have to divide by 3/2, which is the same thing as multiplying by 2/3. So this is 2/3 times u, that's 1 plus x squared, to the 3/2 power plus c. And now we can cancel these 2's, and you get 5 over 3 times 1 plus x squared to the 3/2 power plus c. Now, people always ask me, what happened to that x? There was an x in the original integral. It's gone. We only have a 1 plus x squared with a power. And the answer is nothing happened to that x. That x was incorporated into the differential. If that x had not been there, we could not have done the problem at all, at least not at this stage. Problem 2 actually deals with what are known as simple differential equations, but very simple differential equations. We start with a derivative, f prime of x equals 4x minus 6, and we're asked to find the function f of x, but we're given an extra condition, and that condition is that f of 0 is equal to 3. Now, what are we going to do? This is the derivative, and what we want to do is find the original function. Well, the original function, f of x, is equal to the antiderivative of this expression. What is the antiderivative of this expression? Well, let's write it, 4x minus 6 dx. And what do we have? The antiderivative of 4x, well, the antiderivative of x, you know, is 1/2 x squared. There's a 4 multiplier, so we have 4 times 1/2 x squared minus the antiderivative of the constant 6 is just 6 times x. Is that right? Because the derivative of 6x is just 6. Plus a constant. And that constant is important now, because we now have f of x is equal to 4 times 1/2 is 2, x squared, minus 6x plus c. And here's where that extra condition comes in, because the extra condition we have is that f of 0 is equal to 3, meaning if we substitute x equals 0 into this expression, the result must be 3. In other words, if we put in here x equals 0, we get 3 is equal to, and here we have what? X equals 0 makes this term 0, makes this term 0, so you get 0 minus 0 plus c, and so obviously c is equal to 3. Now, the extra condition determined the value of c. c is 3, and we know that the function we're looking for, f of x, is 2x squared minus 6x plus c, and c we just found to be 3. F of x equals 2x squared minus 6x plus 3. In 2b, we go one step further. We're told that f double prime of x is equal to 3x squared, and we're asked to find the function f of x. This time we're given two extra conditions. One, we're told the value of f prime at x equal 2, and we're told the value of the original function at x equal 1. All right? F double prime x is 3x squared. That means f prime of x is the antiderivative of 3x squared. Now that's so simple I'm not even going to bother writing down the integral. The antiderivative of 3x squared is exactly x cubed plus a constant. Again, we have that subsidiary condition. When x equals 2, f prime is supposed to equal 3. So if I substitute x equals 2 into this expression, I get 3 for f prime. So I have 3 is equal to 2 cubed is 8 plus c, and this tells me that c is equal to minus 5. Now go back. F prime of x is equal to x cubed minus 5. Is that right? X cubed plus c. We just found c was minus 5. F prime of x is x cubed minus 5. Halfway. Now we have to get back to f of x. To get back to f of x, we must anti-differentiate one more time. So f of x is equal to the antiderivative of x cubed by our basic formula is 1/4 x to the 4th minus the antiderivative of 5 is 5 times x, and we have another additive constant. Can I call it c again? Sure, why not? We have 1/4 x to the 4th minus 5x plus c. Now sometimes you have to be careful. Sometimes both constants appear at the same time. Then you ought to call them c sub 1 and c sub 2 or c and k. But here I've already solved for the first one, so there's no confusion. This is a different c, and I have to evaluate it. How do I evaluate it? I use the given condition that f of 1 is equal to 6, meaning if I substitute 1 in here, the answer should be 6. So I have 6 is equal to 1/4 of 1 to the 4th is simply 1/4, minus 5 times 1 is 5, plus c. Now again, I have an arithmetic problem. If I add 5 to both sides, here I'll get 1/4 plus c is equal to 11, and then I subtract a quarter. What's 11 minus a quarter? 10 3/4. 10 3/4 is 40 over 3. So I have 40, did I say that right? 10 3/4 is 43 over 4, and that's equal to c. Final result, f of x is equal to 1/4 x to the 4th minus 5x plus 43 over 4. In problem 3, we're going to look at some definite integrals. Now, a definite integral, take a look at 3a. The integral from 1 to 3 of 3x squared dx. What does that really mean? The definite integral has to be interpreted as follows. We're going to find the antiderivative of what's in here. That's the first step. Then we have to evaluate the antiderivative at each of the two limits and find the difference. I'm going to say that again. Let me write it down in general. If I have the integral of f of x dx from a to b, if I can find the antiderivative of little f of x, let me call it, say, capital F of x, then this is equal to capital F of x evaluated from a to b. And what does that mean? That means substitute this upper limit in here and get f of b, and then subtract from that what you get when you substitute the lower limit, namely f of a. All right? Now this first one, let's go back. First one, we take the antiderivative of 3x squared dx. Picked an easy one for myself. Antiderivative of 3x squared dx, that's x cubed. Limits are 1 and 3. So we go from 1 to 3. Now what do? We substitute the 3. That gives us 3 cubed, or 27, minus, we substitute the 1, that's 1 cubed, which is 1. 27 minus 1 is 26. So this definite integral, the integral from 1 to 3 of 3x squared dx, turns out to be 26. The definite integral works out to be a number, 26. Take a look at part B. In part B, it's just a little more complicated. The lower limit here is minus 3, the upper limit is 6, and we have two terms in the derivative whose antiderivative we want to find. So we have the integral from minus 3 to 6 of x squared minus 3x, the whole thing times dx. Nevertheless, the method is the same. We take first the antiderivative. The antiderivative of x squared is 1/3 x cubed minus the antiderivative of 3x. Well, that's 3 times the antiderivative of x, so that's 3/2 times x squared. And we evaluate this from minus 3 to 6. Now, actually, we've done all the hard stuff already. We've done all the calculus. The rest is strictly arithmetic. Here we go. We substitute the upper limit, and we get 1/3 of 6 cubed. What's 6 cubed? We'll worry about that later. Minus 3/2 times 6 squared. That's evaluated at the upper limit. We subtract from that what we get at the lower limit. That's 1/3 of minus 3 cubed minus 3/2 of minus 3 squared. All right, more arithmetic. 6 cubed is 216. 216 divided by 3 is 72. 3/2 of 6 squared. 6 squared is 36. 36 divided by 2 is 18. 18 times 3 is 54. That's right. Minus 3 cubed is minus 27 times 1/3 is minus 9. And here we have minus 3 squared is plus 9. 9 times minus 3/2 is minus 27/2. I hope some of you have calculators. This is not getting easy for me. 72 minus 54 is 18. And what do I have here when I remove the parentheses? Plus 9 plus 27/2. Okay, 18 and 9 is 27, plus 27/2. That's 54/2 plus 27/2, and that's 81/2. So the integral from minus 3 to 6 of x squared minus 3x dx turns out to be 81/2. 3c, we have the integral from minus 2 to 2 of the square root of 2x plus 5 dx. First, as usual, I'll convert the square root into the 1/2 power. So we'll rewrite this as the integral from minus 2 to 2 of the quantity 2x plus 5 to the 1/2 power dx. Now, this would be in the form u to the half du if this were 2 dx. So we're going to make it 2 dx by simply putting in a 2. But of course, in order to keep everything square, I also have to divide by 2. And I'll do that outside the integral, multiplied by a half. So we now have 1/2 the integral from minus 2 to 2 of 2x plus 5 to the half times 2 dx. And this is precisely u to the half du. And that we can find the antiderivative of. So this is 1/2. Now the antiderivative of u to the half is u to the 3/2 divided by 3/2, or if you prefer, 2/3. U to the 3/2, that's 2x plus 5 to the 3/2 power. And that's evaluated from minus 2 to 2. Now we'll cancel this 2 and this 2, and we have left 1/3. And now we evaluate at the upper limit and the lower limit. So we have 1/3 of, evaluate at the upper limit, 2x plus 5 becomes 4 plus 5 is 9, so that's 9 to the 3/2 power. minus, evaluate the lower limit, 2x is then minus 4. Minus 4 plus 5 is 1. So this is 1 to the 3/2 power. Thus we have 1/3. 9 to the 3/2 is what? That's the square root of 9 cubed. That's 3 cubed is 27. So that's 27 minus 1 to any power is 1. That's 27 minus 1. We have 1/3 of the quantity 27 minus 1, which is 26. So this is simply 26 over 3. In problem 3D, we have another definite integral from 0 to 1 of x squared times x cubed plus 1 to the minus 3 power dx. Again, I would like to have something in the form u to the n du. If I think of x cubed plus 1 as u, then du has to be 3x squared dx. Well, I have the x squared here and I have the dx. So let me write this the way I want it. The integral from 0 to 1 of x cubed plus 1 to the minus 3. Bring this x squared over here and make this 3x squared dx. And of course, don't forget I multiplied by 3, so I have to multiply here by 1/3 so that I haven't changed the integral. This is now 1/3 of, now I have precisely u to the minus 3 times du. And the antiderivative of u to the minus 3 is u to the minus 2 over minus 2. So this becomes x cubed plus 1 to the minus 2 over minus 2, and that's evaluated from 0 to 1. Now let's see. I have 1/3, I have a minus 2 down here, so this becomes minus 1/6, which I'll factor out. And now I evaluate at the upper limit. At the upper limit, this becomes x is 1. This is 1 plus 1 is 2. So this is 2 to the minus 2 power. Minus, evaluating at the lower limit, this becomes 0 plus 1, or 1 to the minus 2 power. And now let's see what the arithmetic works out to. This is minus 1/6 of 2 to the minus 2 is 1 over 2 squared, or 1/4. This is 1/4 minus, of course, 1 to the minus 2 is still 1. 1/4 minus 1 is minus 3/4. So this is minus 1/6 times minus 3/4. That's going to become plus. 3 goes into 6 twice, so that's 1 over 2 times 4, or 8. We'll look at some applications of the integral calculus. The first one that we're going to look at is the problem of finding areas. In particular, we'll start with question 1a, finding the area under a curve. We're given the curve y equal x squared minus 2x plus 3, and asked to find the area under that curve above the x-axis and between the vertical lines x equal minus 1 and x equal 3. Let's take a look at the graph and see what that area actually looks like. Well, here's the graph of the parabola y equals x squared minus 2x plus 3. Here's the vertical line x equal minus 1. Here's the vertical line x equals plus 3. You can see that between minus 1 and plus 3, the entire area lies above the x-axis and below the curve. We know that if we have a curve that lies entirely above the x-axis, we can find the area under that curve and above the x-axis between any two values of x by simply finding the definite integral of that function between those values. Let me just draw a quick sketch of the graph you saw before. It looks like this, and the area we're looking at goes from minus 1 to plus 3. This area can be found by simply taking area equals the definite integral from minus 1 to plus 3 of this equation, or this expression, x squared minus 2x plus 3 dx. Evaluating a definite integral means what? Find the antiderivative, substitute the two limits, and do the arithmetic. So the antiderivative, 1/3 x cubed, antiderivative of minus 2x is minus x squared, plus antiderivative of 3 is 3x, and we evaluate from minus 1 to 3. Substituting the upper limit, x cubed, that's 3 cubed, is 27. 1/3 of 27 is 9. Minus 3 squared is 9. Plus 3 times 3 is yet 9 again. Minus, now we substitute minus 1. Minus 1 cubed is minus 1 times 1/3 is minus 1/3. Minus 1 squared is plus 1. Plus 3 times minus 1, which is minus 3. Cancel these two, plus 9 and minus 9, and remove the parentheses. We have 9 plus 1/3 plus 1 plus 3. And this is equal to 9 and 1 is 10 and 3 is 13. 13 and 1/3, which is 40 over 3. In problem 1b, we're asked to find the total area bounded by the curve y equal x cubed and the x-axis between the two vertical lines x equals minus 2 and x equal plus 1. Now let's take a look at the graph of this area. Here's the graph of y equal x cubed. If you look back here, this is the line x equal minus 2. This is the line x equal plus 1. You can see that the region that we're after is in two parts. There's a region over here between minus 2 and 0 where the curve is below the axis, and the region is bounded below by the curve and above by the x-axis. To the right, we have another region where the curve is above the x-axis, so the area is bounded above by the curve and below by the x-axis. Okay, since part of this area lies below the x-axis, you cannot find the total area by simply taking the integral from minus 2 to 1 of the expression x cubed. Let me just give you a quick picture of the curve again. The area looks something like this. That's not quite as good as we had before, but it'll do. This is supposed to be minus 2, and this is supposed to be plus 1. To the left of the origin, this area is below the x-axis. If we take the integral from minus 2 to 0 of x cubed, we're going to get a number that is numerically equal to this area, but it will be negative. Let me say that again. When you take the integral of x cubed from minus 2 to 0, we're going to get a negative number, but the absolute value of that number will be this area. We can then find the other part by taking the integral from 0 to 1 of x cubed, because in this region, the curve lies above the x-axis. So the total area is equal to the area 1 over here plus area 2, which is over here. To find area 1, we take the integral from minus 2 to 0 of x cubed dx. That's equal to 1/4 x to the 4th evaluated from minus 2 to 0. If we substitute 0, this becomes 0. If we substitute minus 2, we get minus 2 to the 4th, which is the same thing as 2 to the 4th, or 16. 1/4 of 16 is 4. Remember, we subtract what we get at the lower limit, so we have 0 minus 4, and this turns out to be minus 4 as predicted. The value of this integral turned out to be negative. Minus 4 is the value of the integral. The value of the area has to be positive, is the absolute value of minus 4. In other words, area 1 is equal to plus 4. To find area 2, we're going to have to find the same integral, but now over the region 0 to 1. So we take the integral from 0 to 1 of x cubed dx. Again, the antiderivative is 1/4 x to the 4th, and the evaluation now goes from 0 to 1. At 1, substituting, we get 1/4 of 1 to the 4th, which is 1/4, minus now the evaluation at the lower limit, which is 0. Substituting 0 in here, we get 0. So the value of this integral is 1/4. Hence, the integral has value 1/4, which is the same as the area. So area 2 is also equal to 1/4. And the total area, which is what we were after, total area is equal to what? 4 plus 1/4, which is 17 over 4. 1c is just a little bit different. In 1c, we're asked to find the area bounded by two curves. First is y equals x squared minus 4x plus 2, and the second is y equals x minus 2. The first we recognize actually is a parabola, and the second is a straight line. So let's take a look at the area bounded by these two curves. Here we have the graph of the parabola y equals x squared minus 4x plus 2. Here's the straight line, y equals x minus 2. And you can see that the two curves, that is the straight line and the curve, surround an area which has been shaded in for us. If you look at this graph very carefully, you can see that it's so well drawn that we can actually detect what the points of intersection are of the two curves. Over here, this one appears to be at x equal 1, y equal minus 1. And over here, we seem to have another intersection at x equal 4, y equal 2. But we're going to check that one out algebraically. Again, I'm going to do one of my little freehand sketches so that we have something to refer to. Here's the parabola. Here's the line. And here are our 2 points of intersection. Now, first, before we do anything else, we should determine the coordinates of those points of intersection. And how do we do that? We do that by solving the two equations simultaneously. All right? We have y equals x squared minus 4x plus 2, and we have y equals x minus 2. To solve simultaneously, we say that things equal to the same thing are equal to each other. In other words, y is equal to this, y is also equal to this. Therefore, these two right-hand sides have to equal one another. Let's set them equal, and we have x squared minus 4x plus 2 is equal to x minus 2. Bringing everything over to the left-hand side, this gives us x squared minus 4x minus x is minus 5x, plus 2 minus a minus 2, that's plus 2 is 4, and we have x squared minus 5x plus 4 equals 0. That factors x minus 1 times x minus 4 equals 0, and we get that the two values of x where the curves intersect are x equal 1 and x equal 4. Now, strictly speaking, I don't really need the y values in order to find the area that I'm after, but let's find them just for the sake of completeness. We can find the y values by substituting these x values into either of the two equations. Clearly, the second one is easier. If we substitute x equal 1 in to y equals x minus 2, we get y equal minus 1. So at x equal 1, y equal minus 1. If we substitute x equal 4 in here, we get y equals 4 minus 2, or y equals 2. If you remember that nice graph we saw a minute ago, these were exactly the coordinates that appeared on the graph. 1 minus 1 for one point, and 4, 2 for the other. Now, how do you find the area between two curves? Well, there's a special way to do it. If you call the upper curve, say y equal f of x, and the bottom curve y equal g of x, then the area between them is obtained by taking f of x minus g of x and taking the integral between the two x values of interest. Let me write that down in general. If you had, this is f of x, and this one is g of x, and suppose these intersection points were x equal a and x equal b, then the area is equal to the integral from a to b of f of x minus g of x times dx. All right? Let's try to do this for our specific example. The area is equal to, now let's see, what's a and what's b? We started out, the values of x range from x equal 1 at one end of the area to x equal 4 at the other end. So our integral goes from 1 to 4. F of x is the formula for the upper curve, the higher curve, in this case, the straight line. So f of x is x minus 2. G of x is the formula for the lower curve, in this case, the parabola. So g of x is x squared minus 4x plus 2. And there we have the area expressed as a definite integral. Now, if we want to do this problem, what I'm going to do is remove parentheses, combine like terms, and then integrate this expression term by term, as we've done several times in the past. This is integral from 1 to 4, x minus 2. If I remove these parentheses, I get minus x squared plus 4x minus 2 dx. Combine like terms. We have integral from 1 to 4 of x plus 4x is 5x. Minus 2 is minus 4. And minus x squared is minus x squared dx. Algebra's over. Time to use the calculus. We take the antiderivative, and we get antiderivative of 5x is 5 halves x squared. Antiderivative of minus 4 is minus 4x, and the antiderivative of x squared is 1/3 x cubed. Don't forget that minus sign. And this whole thing is evaluated from 1 to 4. I'm running out of room. I'm going to move back up here to the top to finish. I substitute x equal 4 into this expression, and I get 5 halves times x squared. X is 4, x squared is 16, minus 4 times 4 is 16, minus 1/3 of x cubed, and 4 cubed is 64. From this, I have to subtract the value I get when x equals 1. At x equal 1, I get 5 halves times 1 squared, which is 5 halves. Minus 4 times 1 is minus 4, and minus 1/3 times 1 cubed is minus 1/3. Now what I want to do is remove parentheses once again, combine like terms, and finish the arithmetic. 5 halves times 16, that's 8 times 5 is 40. 40 minus 16 is 24. So I have 24 minus 64 over 3. Now in here I have minus 5 halves plus 4 plus 1/3. Almost done. Minus 64 over 3 plus 1 over 3 is minus 63 over 3, which is minus 21. 24 minus 21 is 3. We have a 4 here. 3 and 4 is 7. So I get 7 minus 5 halves, and 7 minus 5 halves is 9 halves. So the total area that we got is 9/2. Now we're up to volumes. Problem 2a asks us to consider the following example. We take the area under the curve y equal x cubed and above the x-axis between x equal 1 and x equal 2 over here, and we're supposed to revolve this area about the x-axis like this. Revolve it about the x-axis, you're going to sweep out a certain volume. And the question is, what is that volume? Well, let's see what happens. If we pick any value of x between 1 and 2, and we construct a little rectangle of thickness dx at that point, we take that little rectangle and we revolve that about the x-axis, and what you get is a solid in space. And that solid is in the shape of a very small cylinder. A cylinder is like, in this case, a disk. It looks something like this. Of course, actually, our cylinder is turned this way as we go around. The volume of a cylinder is the area of the base times the height, or in this case, times the thickness. Now, for our cylinder, the height for any x is this height, the distance from the x-axis to the curve. And that becomes the radius of this base. So the area of the base is pi r squared. It's a circle where r is the distance from the x-axis up to the curve. Or in other words, r is equal to y. Therefore, the area of the base is pi y squared. We then have to multiply that by the thickness of this little cylinder. And the thickness, remember this came from here, that thickness is dx. So the little volume we get is pi y squared dx. And that is our differential of volume, dv. So we have dv equals pi y squared dx. Now we get the volume of the entire region by essentially adding up all these differential of volume. Each of these differentials of volume, of course, really is infinitesimally small. So when we say add them up, what we really mean is find the integral of this expression. Of course, this involves y squared and dx, and we're going to have to express everything in terms of x. But that's easy, because we know that on this curve, y is equal to x cubed. Hence, our differential of volume is pi times x cubed squared dx. X cubed squared is x to the 6th. So dv is equal to pi times x to the 6th times dx. The volume is the integral of dv between the two limits of integration, that is, between the two x values that define the region we're talking about. And those x values are x equal 1 and x equal 2. So we have that the volume is equal to the integral from 1 to 2 of pi times x to the 6th times dx. Pi, of course, is a constant. We can factor pi, find the antiderivative of x to the 6th, which is 1/7 of x to the 7th, and we evaluate from 1 to 2. Substituting x equal 2, we have pi over 7, x to the 7th, that's 2 to the 7th, minus pi over 7 times, evaluate at the lower limit, 1 to the 7th. Factoring pi over 7, we have pi over 7 times 2 to the 7th is 128, minus 1 to the 7th is 1. So our final result is that the volume we're looking for is pi over 7 times 127, or 127 pi over 7. Question 2b asks us to take the same region that we had in 2a, only this time we're supposed to revolve it about the line y equals 10. Now let's take a look at the picture. Here's our curve y equal x cubed again, between x equal 1 and x equal 2, so we have this region. But now we're going to revolve it about this horizontal line y equal 10. Now if you take a little piece, a little sample rectangle at any value x, the same as we did in the previous problem, if we revolve this about y equal 10, what you get is a punctured disk, something like a washer. In other words, it comes around and sweeps through space, so you get a disk with a hole in it. Looking down at it from above, what you would see is something like this. Where this thing actually has a certain thickness. I see my circles are as good as they always are. The area of this washer, this punctured disk, you have to get by taking the outer radius and finding the area of the entire disk, and then take the inner radius and use that to find the area of the part that's been punctured out of it. If you then take the difference between the entire area and the area of the missing section, you will get the area of this ring-shaped object. If you then want to get the volume of that, you simply have to multiply that area by the thickness of the washer. All right? In other words, if I call this distance, say this outer radius distance, r sub 1, and I take this distance, call that the inner radius, r sub 2, then the area of this punctured disk is pi times r1 squared, that's the area of the entire circle, minus pi times r2 squared, where that's the area of the inner circle. Now, how does that relate to our diagram up here? Remember, we take this sample rectangle, revolve it about y equals 10, and we're getting this shape. Now, the outer radius we get from this point down here, because that's going to be the largest circle we get as that goes around, and the outer radius then has got to be the distance from the x-axis up to that line y equals 10, which means for our problem, the outer radius r1 is equal to 10. The inner radius we get by looking at this point, because this whole section is going to give us a void. There'll be nothing there. This is the innermost part of the ring. So the inner radius is the distance from this point on the curve up to the line y equal 10. In other words, the radius r2 is 10 minus y. So the radius is r2 is 10 minus y. Remember, of course, that y on this curve is x cubed. So in fact, r2 is 10 minus x cubed. Now, let's see if we can put all that together. We have the outer radius, we have the inner radius, the area of the annulus, or disk, punctured disk, is equal to pi r1 squared minus pi r2 squared. In other words, the area is equal to pi times 10 squared minus pi times this quantity, 10 minus x cubed, all squared. To get the volume of this disk, we have to multiply by the thickness, and the thickness, again, is this little thickness, dx. So our differential of volume is dv equals pi r1 squared minus pi r2 squared times dx. Substituting in, we have dv is equal to r1 squared is 100, so this is pi times 100 minus pi times and r2 squared is 10 minus x cubed all squared. And this whole thing is multiplied by dx. Again, to find the volume, we have to add up all these differentials, meaning we have to take the integral of dv over the region in question, which is from x equals 1 to x equals 2. So the volume is the integral from 1 to 2. Now here you see we have a pi here and a pi here. Let me factor that pi and put it out in front. The volume is equal to pi times the integral from 1 to 2 of 100 minus 10 minus x cubed all squared times dx. Problem is all set up. Now we do the algebra. After the algebra, the calculus. And after the calculus, the evaluation. So we have v is equal to pi times the integral from 1 to 2. We're going to have to square this. We have 100 minus the quantity, 10 minus x cubed squared. That's 100 minus 20x cubed plus x to the 6th dx. We're going to remove parentheses and combine like terms. And we have pi times the integral from 1 to 2. I don't like the way that looks. The integral from 1 to 2. 100 minus 100 is going to drop out. Minus a minus 20x cubed is plus 20x cubed minus x to the 6th dx. This gives us pi times antiderivative of 20x cubed is what? That becomes x to the 4th over 4, so this becomes 5x to the 4th, and this becomes minus 1/7 x to the 7th, and the integral goes from 1 to 2. Finally, we substitute the numbers. We have pi times, now let's see what we have. When we substitute x equal 2, we get 5 times x to the 4th. That's 5 times 2 to the 4th. 2 to the 4th is 16. 5 times 16 is 80. So that's 80. Minus 1/7 of 2 to the 7th. 2 to the 7th is 128. So that's 128 over 7. Minus the evaluation at x equal 1. At x equal 1, we have 5 times x to the 4th is 5. And then this becomes minus 1/7 of 1 to the 7th, and that's just 1. And now we remove parentheses and combine like terms. We have pi times 80. This is going to be a minus 5 is 75. Minus 128 over 7. This will become plus 1 over 7. So that's minus 127 over 7. And finally, if we combine this into a single fraction, we get 398 over 7 times pi. That's a long problem, but I hope we have the right answer. The total volume is 398 pi over 7. Example 2c asks us to find the volume that we get when we take the same region that we've been working with, but this time revolve it about the y-axis. In particular, we're told to find the volume we get by revolving this around the y-axis by the method of cylindrical shells. Now, what is a cylindrical shell? Well, here's that region again. Here's that curve y equals x cubed from 1 to 2, and we have our sample rectangle vertically going from the x-axis up to the curve. We revolve this region about the y-axis like this. Now, what kind of region in space does this sample rectangle sweep out? Well, it sweeps out a thing that might look like a piece of pipe or possibly the side of a tin can. It's a cylindrical shell. Look down from above, it looks like a circle and a very close to it other circle inside. That is, the region is just a little shell this thick, and it is a cylinder that extends out. Looked at sideways, it looks like this. Now, the question is, how do you find the volume of a region of this type? Well, to find the volume exactly is a little difficult, and it's really not necessary, because this region is so thin that for all practical purposes, we can think of this as almost zero thickness, so that if we slit it open and rolled it out, it would really come out to be flat, in which case the volume would really look like a rectangular solid that would be a flat rectangle of very, very small thickness. You see what I'm saying? If I take this, like if I took the side of a tin can and cut it open, I could roll it out flat and form a rectangle, and the rectangle would look like that. Now the question is, how big is this rectangle? Well, the height of the rectangle is the same as the height of the cylinder. The length of the rectangle is the same as the distance around the cylinder. And if we want to find the area, then we need the height of the cylinder times the distance around the cylinder. The height of the cylinder times the distance around the cylinder. Okay? How high is the cylinder? Well, if we go up to our graph, we see that the height of the cylinder is the distance from the x-axis up to the curve. And that distance is y. So this, on this little rectangle, this distance is y. Now, how far is it around the cylinder? Well, you see, this sample rectangle is at some particular value of x, and when we revolve this around, this distance x is the radius of the top of that cylinder. So this distance is x, meaning the distance around is given by the circumference of a circle whose radius is x. Now the circumference of a circle is 2 pi r. So in this case the radius r is x, and hence the distance around this circle is 2 pi x. Therefore we have this little rectangle, height y, length 2 pi x, area is 2 pi xy. That's the surface area of the outside of this cylinder. The volume of this cylindrical shell is just that area multiplied by the thickness. How thick is it? Well, the thickness is this thickness right here. Now what's that thickness? That thickness is dx. So our differential of volume when we use the cylindrical shell is 2 pi xy dx. Now that's a very nice kind of formula to use, because in most examples functions are given in the form y equals f of x, which means that if we have the area under a curve given as y equals f of x, we can substitute in here 2 pi x times y. Y is an expression in x, and we're directly in the form of the differential of volume 2 pi x times some other function of x times dx. In this case, y is x cubed. So for our purposes, dv is going to be 2 pi x times x cubed dx. Adding up all these differentials of volume, we're going to get the total volume, because adding up all the differentials means integrating. All right? 2 pi x times x cubed, that's 2 pi x to the fourth actually, dx. So our volume is the integral of 2 pi x to the fourth dx. And the limits of integration are the limits of the region. And the region goes from 1 to 2. So this integral goes from 1 to 2. Now this is a nice simple integral which we can do quickly. This is 2 pi times the antiderivative of x to the fourth is 1/5 of x to the fifth, and we evaluate from 1 to 2. All right, we'll factor out the 2 pi over 5. So this is 2 pi over 5 times, we evaluate at the upper limit, that's 2 to the 5th. 2 to the 5th we know is 32, minus 1 to the 5th at the lower limit is 1. 32 minus 1 is 31. So we have 2 pi times 31, that's 62 pi over 5. In problem 2D, we're asked to again revolve a region about the y-axis. This time, it's the region bounded by the y-axis itself, the curve y equals x cubed, and 2 horizontal lines, y equal 1 and y equal 8. So this is the region we want to work with, and we're going to revolve it about the y-axis. Now, my first inclination when I see a problem to revolve something about the y-axis is to try to do it by the cylindrical shells method that we just used. The difficulty with that method here is that if we take our sample rectangle, say over here somewhere, then the height of the sample rectangle will go from 1 to 8. But if we take the sample rectangle for a different value of x, say over here, then the height of the sample rectangle goes from the point on this curve up to y equal 8, which would force us to do the problem in 2 parts. But there is an alternative, and the alternative is to take a sample rectangle that is horizontal. And if we take a sample rectangle that's horizontal, it looks something like this. And when we revolve about the y-axis, we're going to generate a disk again. Only this time, the radius of the disk will be this horizontal distance x, so that the area of the disk is going to be pi x squared, whereas if you look back 2 problems, it was pi y squared when we went about the x-axis. So this is pi x squared for the area of the disk. The thickness of this disk now, you see, is dy, not dx, because now the thin side is in the y direction. So we have this little thickness, dy, and the differential of volume is therefore pi x squared times dy. So we have the differential of volume is pi x squared dy. All right? Y on this curve is equal to x cubed. Since y equals x cubed, we can solve for x in terms of y, substitute into our differential of volume, and we'll have our volume in terms of y instead of x. Now that's really going to be helpful for us because, you see, we were given the limits of the region to be y equal 1 up to y equal 8. So everything is really set up very nicely for us if we do everything in terms of y. Now, how do we solve y equal x cubed for x in terms of y? We simply take the 1/3 power of both sides of this equation. Y equals x cubed is the same thing as x equals y to the 1/3 power. We substitute x equals y to the 1/3 into the differential of volume right here. dv equals pi times y to the 1/3 power squared times dy. Or in other words, dv equals pi times y to the 2/3 power times dy. All right? To find the volume, we're going to add up all these differential volumes. That means we're going to integrate. We're going to integrate with respect to y. So v is equal to the integral of pi times y to the 2/3 power times dy, where y goes from 1 to 8. All right? We factor out the pi. The antiderivative of y to the 2/3, we have to add 1. That becomes y to the 5/3. Dividing by 5/3 is the same as multiplying by 3/5. So we have 3/5 y to the 5/3 power, evaluated from 1 to 8. This is 3/5 of pi, or 3 pi over 5, times, evaluating at 8, we have 8 to the 5/3 power, minus, evaluating at 1, we have 1 to the 5/3 power. This is 3 pi over 5 times 8 to the 5/3 is what? That's the cube root of 8 is 2 to the 5th. 2 to the 5th is 32. So that's 32 minus 1 to the 5/3 is 1. So we have 32 minus 1 is 31. 31 times 3 is 93. 93 pi over 5 is the volume generated. We're going to begin our investigation of the calculus of transcendental functions. The transcendental functions, for our purposes, include the logarithmic, the exponential, and the various trigonometric functions. First, we'll start looking at the logarithmic and exponential functions. The logarithmic function that we'll deal with exclusively is the natural log function. This function and its companion, the exponential function e to the x, are of vast use in engineering, physics, economics, finance, and many, many other fields. We'll start with the logarithmic function, the natural log function. You should know something about the natural logarithmic function from your pre-calculus courses, and you should familiarize yourself with its properties and with its graph before you really begin the calculus of the logarithmic function. However, we'll start directly with the derivatives of the log function. If y equals log of x, dy dx is 1 over x. And if we use the chain rule, if y equals the log of u, then dy dx is 1 over u times du dx. Now let's see how to apply that formula to problem 1, in particular problem 1a. Problem 1a, we have y equals the natural logarithm, ln, of x to the 6th plus 3x minus 2. Now let me warn you that although I'm going to write ln, I may very well say log, because to a mathematician, the only logarithm that he really uses is the natural log. All right? So we have y equals the log of x to the 6th plus 3x minus 2. The derivative, dy dx, or y prime, is equal to 1 over u. This is log of u. U is x to the 6th plus 3x minus 2. So this is 1 over x to the 6th plus 3x minus 2 times the derivative of u. And the derivative of u, this is the chain rule, is 6x to the 5th plus 3. Of course, we could write this as a single fraction, 6x to the 5th plus 3, divided by x to the 6th plus 3x minus 2. Now, moving down to 1b, we have here y is equal to the natural log of 2 plus x squared. We have a function that combines the logarithmic function and one of our old algebraic functions. Since they're combined by addition, we can apply our old derivative rules, which say that the derivative of a sum is simply the sum of the derivatives. So the derivative of this expression is equal to the derivative of log of 2 plus x, which is 1 over 2 plus x, times the derivative of 2 plus x. Now, the derivative of 2 plus x is simply 1. I'll just write that in there so you won't think I forgot it. And that completes the derivative of log of 2 plus x. Don't forget this term. We have to add on to this the derivative of x squared, which we all remember is simply 2x. Again, I could combine this into a single fraction if I chose to, but I don't think I'm going to. I'll let you practice that if you choose. Moving now to 1c, we have, again, y as a function which involves both an algebraic part and a logarithmic part. But in this case, we have x squared times the log of x. That means if we're going to find the derivative, we're going to have to use the product rule. remember the product rule back from part 4. The derivative is y prime equals the first factor, which is x squared, times the derivative of the second factor. The second factor is log of x. The derivative of log of x is 1 over x, plus the second factor, which is log x, multiplied by the derivative of the first factor. The first factor is x squared. Its derivative is 2x. Now, it is traditional. You see, this is very confusing looking. Log of x times 2x. It's hard to know whether it's the log of x times 2x or the log of x, the quantity, times 2x. So it's traditional to put the algebraic part first when we have a product of an algebraic and a logarithmic function. So we're going to rewrite this. First, reducing this, x squared times 1 over x is just x, plus, and now we'll write this as 2x times the log of x. All right? Let's move down to 1D. In 1D, we see we have y equals the square root of 2 plus log x. Now, this is actually a chain rule problem. This is the square root of a certain function. The function that we have under the square root is one of our new logarithmic functions. First, before we take the derivative, we get rid of the square root sign, rewrite, always using fractional exponents instead of radicals. So this is y equals 2 plus the log of x raised to the power 1/2. In this form, we take the derivative using the chain rule. This is some function raised to the 1/2 power. The fact that the function involves a logarithm does not make the chain rule any less true than it used to be. We take the derivative, y prime equals, this is something to the 1/2 power, so the derivative is 1/2 of that expression, 2 plus log x, raised to the power 1/2 minus 1, which is minus 1/2. And then we have to multiply this by the derivative of what's inside those parentheses. The derivative of what's inside those parentheses is the derivative of 2, which is 0, plus the derivative of log x. The derivative of log x is 1 over x. So we have this expression, and let me just simplify that a little bit. I'll combine the 1/2 here and the 1 over x here. Remember, these are all multiplied together. So this is 1 over 2x times 2 plus log of x raised to the 1/2 power, and I see I can't quite read what I've got there, so let me erase that 1 over x and let you see what the answer is. That's y prime is 1 over 2x times 2 plus log x, that quantity, raised to the power minus 1/2. Problem 2 deals with integrals that involve logarithmic functions, or at least logarithmic outputs. The basic formula that we have is that the integral of 1 over x dx is the log of the absolute value of x plus a constant, or the integral of 1 over u du is equal to the log of the absolute value of u plus a constant. Let's take a look at problem 2a. In problem 2a, we have the integral of 1 over x dx. Well, that's our basic formula. That's simply the natural log of absolute value of x plus c. Now, the question really is, why absolute value of x? We know that the derivative of the log of x is 1 over x. So why do we have that the antiderivative of 1 over x is the log of the absolute value of x? Well, the reason is that if x is negative, then the log of x is undefined. But the log of minus x, that is the log of absolute value of x, is going to be defined. And if you take the derivative of log of minus x, you will once again get 1 over x. You should try that or look in your textbook and see how this is derived. The important thing for you to realize is that when you take the antiderivative of 1 over x, you're going to get the log of absolute x. Furthermore, you should realize that 1 over x is the same thing as x to the minus 1 power. which means that we finally filled in that gap in our standard formula for the integral of x to the n dx. Remember, in that case, when we did the integral of x to the n, we always said that n could not equal minus 1. Well, now we've solved that problem. If n is minus 1, then really it's 1 over x, and the integral is log of absolute x plus constant. If we go down to b, you see we have the integral from 1 to 3 of 3 dx over x. Now, what does that mean? 3 dx over x. Well, 3 is a constant and can be factored out of the integral. So we have 3 times the integral of dx over x. Dx divided by x is the same thing as 1 over x times dx. So in fact, this is 3 times the integral of 1 over x times dx, and of course we can't forget these limits, 1 to 3. All right? Now, of course, the integration is easy. This is 3 times the natural log of absolute x. Of course, we don't need the plus c now because we have limits from 1 to 3. We evaluate from 1 to 3, and we substitute. We get 3 times the natural log of absolute value of 3 is 3, minus the natural log of 1. Well, the natural log of 3 is a number. It's approximately 1.1. Actually, to 4 places, I think it's 1.0986. You can check that out with a table, or look it up on a calculator, or you can simply leave it as log of 3, which is really the correct answer. The log of 1, you must remember, is 0. The logarithm of 1 is 0 for every logarithm, in particular for the natural logarithm. So the answer to this is 3 times the natural log of 3. Let's go to part C. In part C, we have the integral of dx over 5x plus 2, and this we're going to have to do by looking for something of the form du over u, and use the formula integral 1 over u du equals the natural log of the absolute value of u plus c. If we want to use that in this example, we have to think of 5x plus 2 as u, which means du would have to be 5 dx. So we'll rewrite this as the integral of 5 dx divided by 5x plus 2. And to make sure we haven't changed the integral, we have to multiply outside by 1/5. 1/5 times 5 is 1, and these two integrals are the same. Remember, you can always factor constants through an integral sign, but not variables. This is equal to now 1/5 of the integral of du over u, so that's the natural log of u. In this case, u is 5x plus 2, so we have 1/5 the natural log of 5x plus 2 plus a constant. If we move down to 2d, we see a similar type of problem. We have 3x times dx divided by 2x squared plus 7, and we want the integral. The only chance we have to do this one is if we have du over u. In that case, we have to let u be 2x squared plus 7. If u is 2x squared plus 7, then du is 4x dx. So let's simply write this the way we want it. 4x dx divided by 2x squared plus 7. Of course, those aren't equal now because this is a 4 and this is a 3. So in order to keep everything right, we multiply out here by 3/4. The 4's cancel, and this is now 3x dx over 2x squared plus 7. Now we have 3/4 times the integral of du over u, which gives us the natural log of 2x squared plus 7 in absolute value plus c. Now in this case, strangely enough, we could actually drop these absolute value signs because the quantity 2x squared plus 7 can never be negative, and that's really the reason that the absolute value signs are there, to protect you against taking the logarithm of a negative number. Since 2x squared plus 7 is always positive, I could drop these absolute value signs, but I won't for consistency. 2e is a definite integral, and it's a tough one. Let's take a look at it. We have the integral from 2 to e of the log of x divided by x dx. Now, although we have a log of x in here, it's not at all clear what we should call u and what we should call du, because there just isn't an obvious thing to call u. In fact, there's no obvious way to make this du over u. However, if we look very closely, we can see the following. This is log of x times dx over x. Written in this form, what you really see is that you have the log of x times the differential of log x. So really you have u times du. Do you see that? In this case, we let the log of x be u, and then du is dx over x. Let me just write that down so we can see it. That's u, and that's du. And now we're really back to those simple algebraic integrals that we started with. The integral of u du is simply 1/2 of u squared. So what I have is 1/2 of u squared, and u is log x. So this is 1/2 of the quantity log of x squared. Plus c? No, because we have limits in this case, so I don't need the plus c. I need to evaluate from 2 to e. All right? I substitute into this expression first the upper limit. That's 1/2 the natural log of e, all squared, minus, notice I factored the half, the natural log of 2, all squared. And I can simplify that a little bit. This is 1/2 the natural log of e. You're supposed to remember the natural log of e is 1. So this is simply 1 squared, or 1, minus the natural log of 2 squared. Natural log of 2, again, you can calculate with a calculator or look it up in a table. It's about 0.7, but we're just going to leave it like this. I should point out that in some books, in some textbooks, you'll find expressions like log 2 squared written this way. Log squared of 2. And you'll have to understand that that means the quantity log 2 squared. That is, the square on the ln means you should apply that square to the expression log 2. However, I'll leave it this way. Now, let's move on to f. And f is really a sneaky-looking problem, but having done e, we've got a pretty good idea how to do it. Here we have 1 over x log x dx. Now, your natural inclination is to say you should call this expression u. That is, the thing in the denominator should be u, so that you'll try to get du over u. But that's not going to work, because the only thing you have up here is a dx. And the derivative of x log x is simply not going to give you 1. But you can use the same kind of trick you just used. Namely, write this as 1 over log of x times dx over x. Now look at what you have. If you now let log of x be u, this is 1 over u times du, because dx over x is the differential of log x. So this is really 1 over u times du. And the integral of 1 over u du is the log of the absolute value of u. So this is the log of the absolute value of u. What did I say u was? U is log of x. So this is the log of x plus a constant. Notice I do have to put the absolute value signs in because the log of x can be a negative number. Whenever x is less than 1, the log of x is negative. This is the log of the absolute value of log x plus c. Problem 3 involves the derivatives of exponential functions, in particular, the function e to the x. If y equals e to the x, dy dx equals e to the x. Now, I didn't make a mistake. The derivative of e to the x is e to the x. It's the only function other than 0 that has the property that the derivative of the function is the function itself. If y equals e to the u, where u is some function of x, then dy dx is equal to e to the u times du dx by the chain rule. All right? Let's take a look at how we apply these simple formulas to problem 3, in particular, problem 3a. In 3a, we have y equals 5e to the 2x power. Well, 5 is a constant, and we know that when we take the derivative of a constant times anything, we just take the constant times the derivative. So y prime is equal to 5 times the derivative of e to the 2x. The derivative of e to the 2x, that's e to the u, so that's e to the 2x, times the derivative of 2x, which is 2. So we have 5 times e to the 2x times 2, in other words, 10e to the 2x. In b, we have y equals the quantity e to the x plus 5x raised to the 10th power. Here we have a combination of the exponential function plus an algebraic function, 5x, raised to a power. So this is of the form y equals u to the 10th power. Now we know how to do u to the n by using the chain rule for powers. So y prime is equal to, this is something to the 10th, the derivative is 10 times that same expression raised now to the 9th power, and then we have to multiply by the derivative of what's inside these parentheses, and the derivative of e to the x plus 5x is e to the x, right? The derivative of e to the x is e to the x, plus the derivative of 5x, which is 5. And our answer is 10 times e to the x plus 5x to the 9th times e to the x plus 5. We can't multiply this into here because here there's an x and here there isn't, so we're going to leave this answer just like this. Moving to C, we have a quotient. Y equals e to the x divided by the log of x. Remember, we got log x in the last problem as one of our integral solutions. Here we have it in the denominator. This problem, we have a combination of the exponential and the logarithmic, and we're going to first have to use the quotient rule. Y prime equals, you remember the quotient rule, we take the bottom, that is the denominator, log of x, and we multiply it by the derivative of the numerator. The numerator is e to the x. The derivative of e to the x is e to the x. So we have log x times e to the x minus the numerator, which is also e to the x, times the derivative of the log of x. What's the derivative of log of x? It's the log of something. The derivative of that is 1 over the log of x times the derivative of what was inside those parentheses. That was log x. The derivative of log x is 1 over x. So here we have e to the x times 1 over log x. That's the derivative of log x. And with the chain rule, the derivative of log x, 1 over x. Finally, to complete the quotient rule, we have to divide by the square of this denominator. And the square of this denominator is the log of x, the whole thing squared. Finally, we go down to 3D. In 3D, we have y equals a product, e to the x squared times the log of 1 plus x squared. Here we have a product of an exponential function and a logarithmic function, and we're going to have to apply the product rule first. But taking the derivative of each of the factors in the product is itself going to be a job. So y prime equals, the product rule, remember, the first function, that's e to the x squared, times the derivative of the second function. The second function is log of 1 plus x squared. The derivative of that is 1 over 1 plus x squared times the derivative of 1 plus x squared, which is 2x. These are all multiplied together. Plus, remember, this was the first function times the derivative of the second. Now we have to do the second function, log of 1 plus x squared, times the derivative of the first function. And the first one is e to some power. And the derivative of e to the u is e to the u times du dx. E to the u, that's e to the x squared, times du dx. U in this case is x squared, and the derivative of x squared is 2x. So here we have a not very nice looking answer, but a correct answer. E to the x squared times 1 over 1 plus x squared times 2x plus the log of 1 plus x squared times e to the x squared times 2x. We could factor e to the x squared times 2x from both terms and simplify the expression. I'm going to let you have a little algebra fun. You can practice factoring and simplify this expression. In problem 4, we'll look at some integrals involving the exponential function. Remember, since the derivative of e to the x is e to the x, then the integral of e to the x dx is e to the x plus c, and the integral of e to the u du is e to the u plus c. If we take a look at problem 4a, we see the integral of e to the 5x dx. In order to make this fit our formula, we want this to be e to the u du. In that case, we want u to be 5x. If u is 5x, then du has got to be 5 dx. So we'll rewrite this as 1/5 of the integral of e to the 5x times 5 dx. Now that's of the form 1/5 integral e to the u times du, and that's simply e to the u. So we have 1/5 e to the 5x plus constant. Moving down to b, we have the integral from 0 to the natural log of 4 of e to the x dx. Well, the integration is easy. The integral of e to the x dx is just e to the x. No plus c because we have limits from 0 to natural log of 4. Substituting the limits, we get e to the natural log of 4 minus e to the 0. And these you should know. E to the log 4 is 4. The exponential and the logarithmic function are inverse functions, so that e to the log 4 is just 4. E to the 0, well, anything to the 0 is 1. So this is 4 minus 1, and the answer is 3. The definite integral from 0 to log 4 of e to the x dx is just 3. Moving now to part C, we have the integral of 3x e to the x squared plus 1 dx. Here, our chance is that we have e to the u du. That is, we let u be x squared plus 1. If u is x squared plus 1, then du is 2x dx. So once again, as we've done so many times, we change this into the integral of 2x e to the x squared plus 1 dx. But of course, that's not right. We started with 3x, now we have 2x. If we want to have the same value, we have to multiply out here by 3 over 2. Now the 2's cancel, and we have 3x, and we're back where we were. But now you see we have precisely e to the u du, although this time the du is kind of separated, 2x dx over here, and the e to the u in the middle, but we can see that. And we have 3 halves. The integral of e to the u du is e to the u. That's e to the x squared plus 1 plus a constant. Finally, we move down to 4d. In 4d, we see that we have the integral of the square root of e to the x plus x times the quantity e to the x plus 1 times dx. Now, the first thing we do whenever we see these radicals is substitute fractional exponents instead. So we rewrite this as e to the x plus x to the 1/2 power times e to the x plus 1 dx. And now we stop and think. Can this possibly be of the form e to the u du? There's an e to the x certainly in the expression. In fact, there's two of them. But I don't see any e to the u du. What I do see is that here we have a certain expression raised to the 1/2 power, and here we have another expression multiplying it. And there's a very nice relationship between these two. This is e to the x plus x, and this is the derivative of e to the x plus x. E to the x plus 1 is precisely the derivative of e to the x plus x. So what I really have here is u to the 1/2 times du. Can you see that? This is u, so this is u to the 1/2, and then this entire expression here is du. So since I have u to the 1/2 du, I can take the integral as an algebraic integral. The integral of u to the 1/2 is 2/3 u to the 3/2. But in this case, u is e to the x plus x to the power 3/2 plus c. That's a tricky one. Look it over again and make sure you understand what we did. We identified this as u, and we noticed that this factor was precisely the differential. So we were able to do the integral as u to the 1/2 du. In this part, we'll be looking at the calculus of the trigonometric functions, in particular the derivatives and integrals of expressions that involve trigonometric functions. We'll start with expressions that involve sine and cosine. The derivative of the sine, it happens to be, is the cosine. And the derivative of the cosine is minus the sine. In symbols, if y equals sine of x, then dy dx is cosine of x. Or if y equals sine of u, then dy dx equals cosine u times du dx. That's using the chain rule. If y equals the cosine of x, then dy dx is minus the sine of x. By the chain rule, if y equals the cosine of u, then dy dx is minus the sine of u times du dx. In problem 1a, we have y equals the sine of 4x. This is of the form sine of u. So y prime, the derivative is the cosine of 4x, that is the cosine of u, times du dx, that is times the derivative of 4x, which is 4. Now, traditionally, people write the algebraic portion in a product before the trigonometric portion. So you'll probably see this answer as 4 times the cosine of 4x. In part B, we have y equals x squared times the cosine of 3x. Here we have a product of an algebraic function, x squared, and a trigonometric function, cosine of 3x. Therefore, if we want to find the derivative, we first must use the product rule for x squared times cosine of 3x before we can start using the new rules that we've learned for the trigonometric functions. Let's try this now. Y prime equals, product rule, we take the first function, x squared, times the derivative of the second function, the the derivative of the cosine of u is minus the sine of u. So this is minus the sine of 3x. And we have to multiply that by the derivative of 3x using that chain rule. So that's times 3. Plus the second expression, cosine of 3x, times the derivative of the first factor, and the derivative of x squared is 2x. Now this is so messy looking. I really would like to simplify it a little bit. First of all, I don't like that minus sign there. Remember, this is a product. This is not x squared minus this. It's x squared times this. So let's bring that minus sign out in front. And we have minus, here's a 3. These are all multiplied together, times x squared times the sine of 3x. And again here, let's put the algebraic factor in front. So we have plus 2x times the cosine of 3x. If we move up to c, we have y equals sine of x plus cosine of 2x raised to the 10th power. Now in this case, we have something of the form u to the nth power. So we're going to have to use our chain rule for functions of the form u to the n. The derivative y prime is equal to the derivative of u to the n is nu to the n minus 1 du dx. So this is 10 times sine of x plus cosine of 2x to the 9th. And we multiply this by the derivative of what's inside these parentheses. The derivative of the sine of x is the cosine of x. The derivative of the cosine of 2x, this is the cosine of u, the derivative is minus the sine of 2x, and then we have to multiply that by the derivative of 2x, which is 2. Now, of course, I really should write that 2 in front of the sine 2x, and perhaps I shall just to make it look a little neater. This is 10 times sine of x plus cosine of 2x to the 9th times cosine of x minus 2 sine of 2x. In part D, we have y equals the logarithm of the sine of x. Now, we did the logarithms in the last section, and you remember that. Y prime equals, here we have the derivative of the log of something, the log of u. The derivative of the log is 1 over that function. So that's 1 over sine of x times now the derivative of u, the derivative of sine x, and the derivative of sine x is cosine x. So this is 1 over sine x times cosine x, and here I can't resist doing a little bit of trigonometry or trigonometric identities that you know. This is the same thing as the cosine of x divided by the sine of x. And if you remember your trigonometry, the cosine of x divided by the sine of x is the cotangent of x. And the cotangent of x is written variously in different textbooks, sometimes COT of x and sometimes CTN of x. So be prepared for your particular textbook, see which notation they're using. At any rate, the derivative of the log of sine x is in fact cotangent x, and that's a nice formula to know because it just might come up in an antiderivative problem. 1e is an interesting looking function. We have y equals sine of 2x divided by 1 plus the cosine squared of x. So we have a quotient, and if we're going to find the derivative, we must use the quotient rule first. Y prime is equal to, remember the quotient rule. We start with the denominator, 1 plus cosine squared x. We multiply this by the derivative of the numerator. Now, the derivative of sine of 2x is what? By the chain rule, it's the cosine of 2x times the derivative of 2x, which is 2. We then subtract from that the numerator, sine of 2x, times the derivative of the denominator. Now let's look at this denominator. This is 1 plus cosine squared x. What does that mean? Well, the derivative of 1 we don't have to worry about. The derivative of 1 is 0. The derivative of cosine squared x. This means the quantity cosine x squared. So really it's of the form u to the second power. So the derivative is 2 times the cosine of x to the first power now, but we then must multiply that by the derivative of the cosine x, because we have cosine squared x, so the derivative of cosine squared is 2 times the cosine times the derivative of cosine. The derivative of cosine is minus the sine. This is a product minus the sine of x. Finally, we finish the quotient rule by dividing everything by the square of the denominator. So we have 1 plus cosine squared x, the quantity squared. Now, of course, in this numerator, here we have a 2 that I probably should move out to the front, and here I have a minus sine 2x, a 2 that should go out to the front. There's another minus in here, so this product really is going to become plus. But again, I'll let you do the simplification. There really isn't that much, because nothing reduces very much.
When you're serious about learning an academic subject or scoring high on a test, there's just one name to know: video-aided instruction. We don't waste your time with goofy skits, corny jokes, or silly sing-alongs. We get right to the point. Real teaching by real teachers. Visit us online at videoaidedinstruction.com to learn more about our exciting line of educational programs. As we say here at Video Aided Instruction, press play to learn.
Do you want to earn better grades in school or boost your scores on standardized tests? Do you want to increase your fluency in English or improve your communication skills at work? Or do you simply want to relearn those forgotten grammar rules? Well, look no further. Video Aided Instruction's English Grammar Series is a great resource for everyone, whether you're new to English or you've been speaking it for years. Our one-of-a-kind series can help you master even the most complicated grammar topics. Be sure to view the entire series: English grammar sentence structure, parts of speech, sentence complements, verbs, pronouns, agreement, modifiers, parallel structure, punctuation, and spelling and capitalization. So don't let mistakes in English grammar embarrass you or hold you back. Let Video Aided Instruction help you eliminate them from your speaking and writing forever. Do you want to get your GED? Well, you're in luck. Video Aided Instruction makes it easier than ever before. Our one-of-a-kind series prepares you for even the toughest questions on the 5 GED tests. Be sure to view GED Language Arts Reading, Language Arts Writing, Mathematics, Science, Social Studies, and Calculator Essentials. Let us guide you toward that all-important diploma, a better job, and of course, higher self-esteem.
If you find studying for the GED overwhelming because you don't have basic reading, writing, or math skills, then Video Aided Instruction's Pre-GED series is exactly what you need. This series makes the fundamentals much easier to understand and master. You'll want to view Pre-GED Language Arts Reading, Language Arts Writing, Mathematics, Science, and Social Studies. Our Pre-GED series is a great first step toward GED success.
A true industry pioneer, video-aided instruction was founded in 1983 by two former teachers from the New York school system. Over the years, our academic courses and test prep reviews have helped millions expand their knowledge and improve their lives. Today, our state-of-the-art studio and production facility is located in Hicksville, New York on scenic Long Island. Educators and students the world over recognize the video-aided instruction brand of academic instruction as the most comprehensive available. Whether you want to brush up on your algebra or improve your skills in English, earn your GED or ACE the SAT, serve your country in the military or pursue a graduate degree, or learn a wide variety of other subjects, video-aided instruction has a program for you.